This lesson will discuss continuity. In order to understand the concept of a limit, we have used the concept of continuity. In fact, the original explanation of a limit was, a limit doesn't tell you what the value of a function is, but rather what it should be in order to produce a continuous curve. So the concepts of limits and continuity are inherently related. In this section, we'll learn more about their relationship. Consider holding a string between two hands. We know that the string is continuous between these 2 points because it's fully connected between our hands. But if we cut the string at any point, we create a discontinuity and the string falls. This illustrates an important principle in mathematical continuity because even though it may seem paradoxical, we define continuity at a single point instead of at a range of values. This is because it only takes a single missing point to make a curve discontinuous. That's why the string will fall when you cut it at one single point. Also consider the fact that a limit is an observation as to what multiple values along the curve are approaching. So we really are considering more than just one point when we involve a limit, regardless. Let's examine the different situations where discontinuities can occur and try to draw some conclusions. The first case that I'm going to look at, I have a graph with a discontinuity, which is a hole in the graph. So the first case that we'll label here is what happens with a hole. So a hole is a discontinuity, and it's just like if I'm holding the string and I cut it. So technically there's no, like the hole is just a missing value. It's not a small circle in the graph. It's a missing value altogether. It's just highlighted by the circle. But let's investigate what happens when we have a hole in the graph. So one thing that happens is the function itself, I'll just call this point A, even though you can see at the value here for this function it's actually at 2. I'm just going to say some point A. F at this particular point does not exist. So if it does not exist, that is an indicator that we have a discontinuity. So if the function does not exist at a point, it's discontinuous there. What about the limit? Since this is a hole, if we approach this limit value from the left and then approach it from the right, the y values approach the same number. And so what happens is the limit as x approaches a of my function does exist, and it happens to be equal to a. So the problem, though, is one of these two values did not exist. So let's look at other situations. The next case that we'll discuss is an asymptote. We can call it an asymptote, but sometimes we talk about holes versus poles. Okay? But it is an asymptote. What happens here is at this particular point, and again I'll just call it some value a along a curve, is, well, first off, the function itself is not defined. It would result in division by 0 possibly, or a logarithm also has an asymptote, but there's some reason that this function does not exist here. So the function itself does not exist. But then also, when I observe the limit from the left and the limit from the right, the limit from the left goes to infinity. The limit from the right of this particular graph is also going to positive infinity. It really doesn't matter particularly that it's going to positive infinity, because recall we said that if it goes to infinity, if the limit goes to infinity, the limit does not exist. That's what we are saying here in this case. So the limit as x approaches a of my function also does not exist. Okay. Let's see if there's other ways that we can get discontinuities. Well, right here is a particular situation that we could have a discontinuity. And this is called a jump in the graph. And when we have a jump in the graph, what happens there is, first off, if you'll notice, I'll call this point A again. F of A actually does exist. And the reason that the point evaluated, or the function evaluated at A exists is because I have this solid circle right up here which gives me the existent value, and if I look across on the y, that tells me the y value that it corresponds with. So f of a actually does exist here. However, if we take a look at the limit as x approaches a of this particular function, what we can see is that as we approach a from the left and we approach a from the right, the y values are approaching different values. So that's telling me that the limit itself does not exist. Right, so now we have a situation where the function does not exist, but the limit does. Neither the function nor the limit exist. And then the function exists, but the limit does not exist. There's one other situation, and that's this situation. We haven't run into this and so far, I don't believe, but it's something that could potentially occur. It's a situation where the function itself does exist. So I'll call this a again. So f evaluated at a exists. So it looks like it would be about 1 on the y-axis scale, but that's irrelevant in the example I'm trying to portray here. It's that it exists that matters. Then the limit as x approaches a of my function also exists. So we have existence in both situations. And it exists because the limit from the left, the limit from the right, they both approach the same y values. However, it's still discontinuous. The reason that we have a discontinuity here is that the limit as x approaches a of my function does not equal what the function is supposed to be at that particular point. So our definition of a limit was the limit tells us what the function should be in order to produce a continuous curve. So in order to have continuity, what the function should be and what the function is have to agree with one another in order to get continuity. And so the thing that's falling apart here is that what the limit is, which is the function, and what the limit should be, which is the limit, disagree with one another. And those are all the different cases that we can have for functions when it comes to discontinuities. So let's go ahead and define then what we mean by continuity. A function f is said to be continuous at the point x equals a, provided that 1. The limit as x equals a of your function exists, so the limit must exist. The function evaluated at that point has to also exist, but also the limit as x approaches a of the function has to equal the function itself. So that's how we know that a curve is continuous at a particular point. Another thing to mention here is if at a particular point of discontinuity the limit does exist. So case 1, the limit does exist, but it's discontinuous because the function does not exist there. And in case 4, the limit also existed, but the limit and the function did not agree with one another. But in cases 3 and 2, where we had a jump or an asymptote, the limit did not exist. So in cases 1 and 4, we can call those removable discontinuities. And the reason that they're called removable discontinuities is because there is a single point that we could put into the function that would make this a continuous curve. So if we put that single point in these two cases, it would now be a continuous curve. So we removed the discontinuity. But if you have a jump, there's not a single number that you could put in, because you'd have to put a whole range of values in to make it continuous. And similarly for the asymptote, you can't put a point at infinity in. That just doesn't make sense, because wherever you place it, there's something above it somewhere else. So if you have a discontinuity and the limit exists, you call that a removable discontinuity. If you have a discontinuity and the limit does not exist, then that's called a non-removable discontinuity. Some questions that you'll run into in your homework are asking you to discuss the continuity of a function. And I want to tell you what that means so that you understand what you're being asked in those sorts of questions. To discuss the continuity of a function, that means to identify where the function is continuous or identify any locations of discontinuity. Then also you want to label any discontinuities as either removable or non-removable. So for all the functions that we've seen so far, they're all continuous on their domain. So finding where a function is continuous is equivalent to finding the domain of the function, which means we're looking for things like locations where division by 0 can occur. That's where we could potentially have asymptotes. Those would be values that are discontinuous, where even roots of negatives could occur, where logarithms of negatives could occur, or 0 as well. Or if you have a piecewise defined function where the two continuous functions join together, there could be a potential discontinuity there as well. So let's do some examples. So let's discuss the continuity of the following functions. First, y equals the sine of x. Now the function sine is not going to involve any sort of division by 0, logarithms, not a piecewise, and so the domain of the function sine is negative infinity to positive infinity. So you can put any value into the function sine and you get a result back out. There is a range restriction, so all the values of sine are in the range of -1 to +1. But the domain, you can put anything you want into the function sine. So what that means is this function is continuous everywhere. And you can say that by just saying it's continuous everywhere, or you can say it's continuous on the interval from negative infinity to positive infinity. Okay, let's try y equals the tangent of x. Well, the tangent of x is different because the way we define tangent is it's the function sine divided by the function cosine. So there's potential for division by 0. In fact, there's a lot of places where we could have division by 0. Division by 0, this could happen anywhere the cosine of x is equal to 0. And to find out where that's happening, if you remember these points without using your unit circle, that's fine, but if you draw out a unit circle, that's fine as well. So you have values of sine and cosine being 1 and 0 at quadrantal angles. So just your unit circle, just think of, all right, this particular point right here would be 1, 0. This point would be at 0, 1. -1, 0, and 0, -1. So the points where cosine is 0 are the points where your x-coordinate on the unit circle is 0. So that's going to happen at pi over 2 and 3 pi over 2. But that's only in the range of 0 to 2 pi. There isn't really a restriction given to us on x at this particular point. So it really could be any multiple of pi over 2 or 3 pi over 2. So this function has removable discontinuities, my apologies, non-removable discontinuities, and the reason I know that they're non-removable discontinuities is because division by 0 is occurring, and therefore we have asymptotes. So it has non-removable discontinuities at x equals, I need odd multiples of pi over 2. So I'll say 2n plus 1 times pi over 2, where n is an integer. It has to be odd multiples, because if I make it an even multiple, then I could get like 2 pi over 2, which would be pi, which is not a place where I would have division by 0. Also, if I allowed it to be 0, which is an even number as well, then I would be over here. So I just need odd multiples of pi over 2. So if you let n be an integer, then 2 times n guarantees that you have an odd value, and then one more past that, 2 times n guarantees that you have an even number. One value past an even number is always an odd number. So at odd multiples of pi over 2. Next up, f of x equals 5 divided by x plus 1. Well, one thing that we're looking for with problems in the domain are points where division by 0 could occur. And clearly we have a point where division by 0 occurs with x equals -1. And that is not a shared factor in the numerator and denominator. So it's going to be an asymptote, which means I would have a non-removable discontinuity at x equals -1. But my function would be continuous on the interval from -infinity to -1, but not including -1, and then from -1 to positive infinity. The next type of an example, I'm going to do a piecewise defined function, because with piecewise defined functions, oftentimes the individual functions are continuous everywhere, but there could be a potential discontinuity where we try and join two functions together. So effectively what we need to do is just determine what's happening with the limit from the left and the limit from the right, see if it's discontinuous, if there's a jump in the graph. So if we look at the limit as x approaches this boundary point of 2 from the left, well, from the left-hand side, we're looking at values that are less than 2. So that means I'd be evaluating at the function x plus 1. So I would do 2 plus 1, which is 3. Then, if I did the limit from the right, so the limit as x approaches 2 from the right-hand side of this function, well, from the right-hand side, I'm looking at values that are larger than 2, but getting smaller and closer to 2. So I have the second function where x is greater than 2. And that's just a constant function, 5. So the result is 5. So these two, the limit from the left and the limit from the right, do not agree. So that means that the limit as x approaches 2 of my function does not exist. So we have a non-removable discontinuity at x equals 2, and therefore we are continuous on the interval from negative infinity to 2, and then from 2 to positive infinity. But I'm not including the 2 on either side. And if you're wondering why I didn't state the interval for which the tangent function was continuous, it's that I had an infinite number of non-removable discontinuities, and so I would have to have written out an infinite number of sets. So it's fine to just mention where it's discontinuous and label what they are in that case. Here's another example with a piecewise defined function. It asks us what value of k is needed in order to produce a piecewise defined function that is continuous. So this is kind of interesting. What we are doing with piecewise defined functions is we're making a boundary point where one function stops and the other function begins. And where we choose that boundary is going to make a difference as to whether we end up with a result that's continuous or not. So in order to do this, let's look at both of the graphs of these functions together on the same axes, and see from there if we can decide where a good point would be to create a continuous curve. So if you'll notice, so the x squared minus 2x minus 4 is the parabola, obviously, and 2x minus 8 is the line. The point that's going to be useful is going to be where they intersect. So I need the first function to continue up until this point, and then I need my second function to begin from here and go on. So whatever this value is right here, this is the value of k that I'm looking for. The question is, how do I solve for it in this particular case? Well, when you have two functions that intersect one another, it means that their graphs share the same x and y coordinate pair. So the same xy value occurs in both of these. And we know that all the y values from the parabola are described by the function x squared minus 2x minus 4, and all the y values of the line are described by the function 2x minus 8. If we want our x and y values to be the same, then assume that you have the same y value and set each of these functions equal to one another. So I could say I need 2x minus 8 equal to x squared minus 2x minus 4. And if you set two functions equal to one another in this way, you can always determine where they're intersecting. So let's do a little bit of algebra. So I will first off subtract 2x from both sides, and then that will cancel these out, and minus 4x here. And then next what I'm going to do is add 8 to both sides so I can get this canceled out. That'll be equal to 0. But I have to add 8 to this side as well, so plus 4. And the reason I got everything set to 0 is because when you have a quadratic, that's what you need to do. You need to get everything set equal to 0 so that you can factor. And it looks like this should be 2 and 2. If it's negative 2 for each one, that'll be great. So I have 0 equals x minus 2 quantity squared. If I then take the square root of both sides, the square root of 0 is still 0. And I can finish this off by adding 2 to both sides. So if I add 2 here and add 2 there, that cancels, and I get x equals 2. So x equals 2 is the x value where these two functions intersect. So that tells me k would have to be 2. So if I made this instead x is less than or equal to 2 or greater than 2, then I now have a piecewise defined function that would be continuous. The intermediate value theorem. The intermediate value theorem says that if f is continuous on the closed interval from a to b, and y equals k is any number between f of a and f of b, then there exists some value x equals c that's between a and b. So the key here is continuity, because if a function is continuous, we know that there's no asymptotes, there's no breaks, there's nothing that's going to be, it's very predictable, okay? And let me graph some general function and help you understand what the rest of this is actually saying. So if I have some function, and I will draw a function like this. So this is my f of x. Now, it's restricted to an interval. So I'm going to make an interval starting with a and ending over here with b. Now, it's a closed interval, so the endpoints are included here. Now, actually, I'll indicate that like this. Okay. So I have a continuous function on a closed interval from a to b. Now, it tells me that y equals k needs to be a number between f of a and f of b. F of a and f of b, these are going to be the y values associated with the points a and b through the function f. So let's say, for instance, I calculate f of a. That would be this point right here. That's f of a. So the y value associated with that x value. And then f of b is this point up here. So the y value associated with the point x equals b. Now, k is a y value, so it's on the y-axis, but it's a number between f of a and f of b. So I'm going to pick some value k. I'll just pick it right in the middle, and that's fine. So I'm going to pick some value k, and as long as this function is continuous and k is between these two values, then there has to be some number c that exists between a and b. That's all this function says. And it should be rather intuitive. You can try different points, but it just means there is always an x and y pair somewhere between these two particular values. The way that we use the intermediate value theorem is often through proving the existence of zeros on a particular interval. So, for instance, if I have a function f of x equals 1 minus 2x, and I observe that f of negative 3 is a positive result. Okay, so if I took f and evaluated it at negative 3, I would have 1 minus 2 times negative 3. So that is 1 plus 6, which is 7. So that's a positive answer. And I observe that at x equals 2, 1 minus 2 times 2 would be 1 minus 4, which is negative 3. So I have a positive result and a negative result. And this is a continuous function on the interval from negative 3 to positive 2. What that means is there must be a 0 somewhere on the interval from negative 3 to positive 2. And negative 3 and positive 2 are not unique values here. I could have used a lot of different values to prove that there's some 0 on an interval, between where x, I just need an x where f is positive and an x where f is negative. Let's look at its graph. Of course, it's a line, and I have negative 3 right here on my x. So at negative 3, what we see is the graph is at 7, just as we predicted, but it's a positive value. And then where x is 2, here is my function down at negative 3, just as we expected. But the point is, it's negative. So what that means is, for any value k that is between a positive number or a negative number, which in this case is 0, there has to be some place where this function crosses the x-axis. So you can't go from positive numbers to negative numbers without passing through 0 somewhere. It doesn't tell you where that somewhere is. It just tells you that it existed someplace between those two values. It looks like it's about negative 1/2. You would have to do other types of tests to determine where that it is exactly, but you've at least proven that that value actually does exist, because you can't go from positive to negative without crossing through 0, and you can't go from negative to positive without crossing through 0. That's what the intermediate value theorem tells us.